Okay, aloha Hawaii. I'm Dave Aronson, the T-Rex of Codosaurus LLC, and I flew over here on my pet pterodactyl to teach you how to kill mutants. So what are those? In our universe, that of software development, not comic books, there's something out of mutation testing. So what on Infinite Earths is mutation testing? You might look at the name and think it's a way to test the mutations used in genetic algorithms or something, but no. It's actually a way to test both our code and our unit test suite by using mutations. Its most unusual benefit is to help ensure that our tests are strict by finding the gaps that let our code get away with unintended behavior. Lack of this strictness usually comes from lack of tests, of course, or poorly written tests, or tests that were poorly maintained and just didn't keep pace with changes in the code. Speaking of the code, mutation testing can also help ensure that our code is meaningful, by which I mean that any tiny little change to it should have a noticeable effect on its behavior. Lack of meaning usually comes from code being redundant or unreachable or otherwise not having any real effect. Mutation testing puts these two together by checking first that some tiny little change did indeed have a noticeable effect, and then that our unit test suite spots that change and fails. Now, not all the tests have to fail, but each change should make at least one unit test fail. Now that's the plus side, but as Fred Brooks told us back in '86 and Malte reminded us the other day, there's no silver bullet. Besides which, they're for killing werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU and therefore usually rather slow. We don't want to mutation test our entire code base on every save. Maybe over a lunch break for a small system or overnight or over a weekend for a larger one. Fortunately, most of the tools do include an incremental mode, so we can test just what we changed since last time. That maybe we can do on every save if we save early, save often, like we know we're supposed to, but don't always. Another drawback is that it's not at all a beginner-friendly technique. It tells us that some particular change to the code made no difference to our test results, but what does that mean? You'll find that interpreting the results of mutation testing involves a lot of asking, so what does that mean, recursively? It takes a lot of interpretation to figure out what a mutant is trying to tell us. They're almost as incoherent as zombies, but with a much larger vocabulary. They're not always on about brains. They're usually trying to tell us that our code is meaningless or our tests are lax, or of course both, but it can take a lot of time and effort to figure out exactly how. And sometimes it's a false alarm. For instance, the mutant might not have made any test fail, but it might not have made any actual difference in the code's behavior either, at least not in anything we actually care about. So those are the main pros and cons, but what does mutation testing actually do? It mutates, hence the name, copies of our code to create test failures, otherwise known as faults. So mutation testing is a fault-based software testing technique, and this means it's sort of related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey uses faults to help Netflix discover flaws in their error recovery process, mutation testing uses faults to help us discover flaws in our code and our unit test suite. But the way this works is kind of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. If the customers don't notice and the metrics still look fine, then Netflix knows that their error recovery is working great. But mutation testing injects instead not faults, but changes. It doesn't know whether these changes will produce faults or not. We hope they all will, but that's actually up to the unit test suite. It injects them not into our actual network, but copies of our code. And it does this in our test environment, not production. Whew. And if everything still passes, that doesn't mean everything is okay. That's when we have a problem. Remember, each change should make at least one unit test fail. So how does it do all of this? Let's peel back one layer of the onion and look at it from a high-level view. First, our chosen tool breaks our code apart into pieces to test. Usually these are going to be our functions. For each function, it then tries to find the tests. As if there aren't any tests, well, it would be kind of redundant to, well, more impossible to run its tests. Assuming it finds any, then the tool makes mutants out of that particular function. And to do that, it looks closely at the function to see how it can be changed. And for each way that function can be changed, the tool makes one mutant with just that one change in it. After the tool's done creating all the mutants it can from a given function, then it iterates over the list. And now we get to the heart of the matter. For each mutant made from a given function, the tool will run the unit tests from the original function, but using a mutant instead. And if one of those unit tests fails, this is called killing the mutant. Quick side note, some people object to the violent nature of this metaphor, especially since in the comic books, mutants are often used as a metaphor for marginalized people. I'm trying to come up with a better term, like maybe cover or rescue or some such, but I couldn't come up with something good in time to change this talk. Oh well. Anyway, killing the mutant means that the tiny little change that the tool made in order to create the mutant did indeed have a noticeable effect on the behavior, and our test suite was strict enough to notice that change and fail at least one test. After one test has failed, the tool will stop running tests against that mutant and move on to the next one. We don't care how many more unit tests that mutant might make fail. Like so much else in computer science, we only care about ones and zeros. But if a mutant lets all the function's unit tests pass, then it has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless, or our tests are lax, or both, and now it's up to us to figure out exactly how. Now let's peel back another layer of the onion and look at some technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree, or AST. I think those were mentioned on Wednesday. I know these boxes are a little small to read, but we don't need to actually understand this AST in detail. After our tool makes an AST out of our code, then it traverses that tree, looking for subtrees that represent our functions. After finding them, it handles them pretty much like I described earlier, starting with looking for the tests. But how does it do that? This usually relies on us developers either annotating our code or following some kind of naming convention. And this is sometimes supplemented or even replaced by the tool looking at what functions each of the tests call. Next, the tool makes the mutants. And to make them from an AST subtree, it then traverses the subtree just like it did to the whole thing. But this time, it's not looking for even smaller subtrees, twigs or something, to extract, but nodes where it can change something, like maybe substitute a different kind of node or whatever. For instance, suppose our tool was traversing the AST I showed earlier, and it's gotten down to this not equals comparison following those red lines. For each way it can change that node, it will make a fresh copy of that entire subtree with just that node changed in that one way. After it's done making as many copies, which are the mutants, by mutating that node, it'll continue traversing this subtree and do likewise to the rest of the nodes. Now, I've been talking about it making changes, so what kind of changes am I talking about? There are quite a lot. It can change a mathematical, logical, or bitwise operator from one to another. In cases where you can do one of a totally different category, it can even do that. For instance, in JavaScript, we can treat anything as Booleans. So x times y could become x and y. It could swap the order of operands in cases where that matters. It can change a comparison from one to another. It could insert or remove a logical negation. It can remove a condition or a loop. It could scramble or truncate the argument lists of function calls or function declarations. It can replace a function's entire contents with returning a constant, returning either of the arguments, deliberately raising an error, all kinds of things, even nothing at all if the language permits, and JavaScript does. It could change a literal or a variable or an expression or a function call to some other value, even one of a completely different type, like changing a number to, if I may quote Smeagol, string or nothing. There are many, many more, but I trust you get the idea. From here on, there are no low-level details I want to add, so let's look at some examples. We'll start with an easy one. Suppose we have a function like this. Think about what a mutant made from this could return, because that's what our unit tests are almost certainly looking at. This doesn't seem to have any side effects. Mainly, such a mutant could return results such as any of these, and many, many more, but I had to stop somewhere. Now suppose we have one test, like so. Yes, this is a rather poor test, but even so, the vast majority of these mutants, well, the mutants that would return these results, would still get killed by this test, the ones shown here in crossed out green. But addition, multiplication, and exponentiation in the reverse order all still get us the correct answer and would therefore survive the test. We know this because when we run our tool, it usually gives us a report that will look kind of sort of like this. The exact format and amount of context and so forth will vary enormously depending exactly what tool we're using, but the information should be pretty much the same. And that is that if we change the function called power, which is in file demo.js at line 42, in any of 4 different ways, all its unit tests would still pass. And then that those 4 ways are to change line 42 to swap the arguments, line 43 to change the exponentiation into addition or multiplication, or line 43 to swap the operands. So what is this set of surviving mutants trying to tell us? A good start to figuring that out is to ask ourselves, how are these mutants surviving? And the usual answer is, well, they give the same result or have the same side effect as our original code. To determine how that happens, a good start is to look at one mutant along with one test that it passes. So let's start with the plus mutant. Looking at this in combination with the test makes it pretty clear that this particular mutant survives because 2 plus 2 is the same as 2 to the second power. So in order to kill this mutant, or cover it, rescue it, whatever, we need to have at least one test that uses inputs such that x plus y is not the same as x to the y. We can either add a test or tweak our existing test to maybe something like this. 2 plus 4 is 6, which is not 16, so this will kill the plus mutant. Better yet, 2 times 4 is 8, also not 16, so as a side benefit, it kills the times mutant as well. But the argument swapping mutants still survive. But that's okay. We don't need to be a superhero about it and kill them all at once. We can attack them separately. To do that, we can once again either add a test or tweak our existing test, maybe to something like this. 3 squared is 9, which is not 8, so that will kill the argument swapping mutants. But also, 2 plus 3 is 5, 2 times 3 is 6, both of those are not 8. So the other mutants stay dead, so we don't get any zombie mutants. With these inputs, the correct operation is the only simple common one that will get us the right answer. This may make mutation testing sound pretty simple, but this was a downright trivial example, so we could easily think up test inputs to make pretty much any reasonable mutant give different results from the original. We could use, for instance, 3 to the 5th or vice versa, whatever. There are lots of ways to skin that flurkin. So let's look at a more complex example. Suppose we have a function like this. Send message, uses send bytes to send as many bytes as send bytes can handle, over and over, picking up where it left off last time until the message is all sent. A fairly common pattern. Now, a mutation testing tool could make lots and lots of mutants out of this, but the one I want to show you is this. It's an example of removing a loop control by deleting those 2 lines with the minus signs there. Now, suppose that this mutant survives our test suite, which consists mainly of this. There's a little more that I'm not going to show you quite yet, dealing with setting the size and creating the message, but even just the fact that this mutant survives tells us something. And that is that if a mutant that only goes through this loop body once has the same result as the original code does in the tests, then our tests are only making the code go through the loop body once. So what does that mean? It means that we're only testing sending a message small enough that send bytes can handle it in one chunk. The most likely cause of that, in turn, is that we're just not sending a big enough message to make it go through the loop body twice or more. Such as, in this case, we might have a maximum chunk size, what send bytes can handle in one shot, of 10,000 bytes, yet we're only testing with a tiny little 3-byte message. And there, the fix is pretty clear. We can just construct a larger message, take the size, add 1, make that big a message, and there we go. But maybe it's not this particular cause. Maybe we did test with the largest permissible message out of a predefined set of messages, or at least message sizes. For instance, here we have small and large sizes, and we did test with a large, and yet the mutant survives. In other words, we're still only going through that loop body once because send bytes is handling the whole message in one chunk. So what's the mutant trying to tell us now? Now it's trying to tell us that a version of send bytes with the looping removed will do the job just fine. And if we do that and then remove everything else that makes redundant, we wind up with this. And now it's pretty clear that the ultimate message is that the whole send message function may well be redundant. Now, I say may well be rather than is, just because in real world code, there may be some logging and error handling and whatnot we need to put in send message. But at the very least, the looping was redundant. Fortunately, when it's this kind of case, the solution is clear and easy. Just get rid of all the extra stuff the mutant didn't have. That will also make our code more maintainable by getting rid of unnecessary cruft. So to summarize, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. But it's not so easy. Oh, sorry, one more thing that is easy. It's easy to get started with in terms of setting up the tools and, if need be, annotating our tests, which may be tedious, but at least it should be easy. But it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean that it might not be appropriate for our current projects right now, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of ones for popular languages and platforms, and some other ones. I doubt many of you are doing Fortran 77 these days. As for JavaScript, the only one I know of is Striker. There used to be one that was a plugin for the Grunt task runner, but that project has folded and its code has been migrated into Striker. Anybody still need some time to take pictures? I saw some cameras up there. Okay, lastly, a couple shout outs. First to TopTal, a consulting network I'm in, whose speakers network helped me prepare and practice this presentation. Please use that referral link if you want to hire us or join us. And secondly, to Marcus Sharp, creator of Mutant, a mutation testing tool for Ruby. It's the main one I've actually used. He's been very willing to answer my ignorant questions, there being no such thing as stupid questions, and critique this presentation, at least the longer forms. This is the shortest one I've done so far. And if you have any questions, well, we're not supposed to do Q&A, but I'll be around for the rest of the conference, and there's my contact information. So mahalo, and let's go get some lunch.